Hello, physical science class. This is your 18B notes section. As we talked about yesterday, we're going to look at the different types of bonds a little more in detail. We're going to start today with our covalent bonds. A covalent bond exists between only two atoms, but an atom can form multiple covalent bonds at the same time, right? We can have a sharing of electrons between several non-metals, all at the same time. So think about it like you have a central element that's bonding on either side with separate elements. Okay. Bonding pairs. We talked about a couple of things in the last chapter related to electron dot notations, which show the number of valence electrons. Remember, in our electron dot notations, we don't show all of the valence electrons that could be. Instead, we only show those valence electrons that this particular element has, right? Like for example, calcium has 2 valence electrons. So our dot notation is going to only show those 2 valence electrons. We're going to build on that because a Lewis structure shows how you have the bonding going on, because you have multiple elements that are sharing or helping each other out by sharing a pair of electrons, right? So a Lewis dot structure would show chlorine, which is in group 7A, therefore it has 7 valence electrons, combining together with another chlorine, also having 7 valence electrons. And when they share, they're going to show how they share a pair of electrons, right? And so you could also write it this way. This is how I would prefer you to think about it for right now, because it helps you to visualize them sharing a pair of electrons. Okay, this would be an example of something that we would call diatomic. Diatomic means you have 2 atoms of the same element and they're bonding together. A single bond is going to be the sharing of just one pair of electrons. Chlorine, hydrogen, different elements that would share one pair with another of chlorine or another of hydrogen. Double bonds means you would share 2 pair of electrons, and triple bonds sharing 3 pair of electrons. So I want to kind of just focus on this diagram. It comes from your textbook. Hydrogen bonding to another hydrogen, sharing just 1 electron to give a single bond. Oxygen tends to find other oxygens, right? Oxygen, O2, this is the breathable oxygen in our atmosphere. Oxygen binding with another oxygen, but I want you to think about the fact that this oxygen has only 6 valence electrons, right? And so it's got to share 2 pair of electrons in order to get its full octet, right? It's a double bond by sharing 2 pair. And nitrogen, notice it has only 5 valence electrons. So nitrogen sharing with another nitrogen, in order to be most stable, is going to have to share 3 pair to get its octet, right? So it would be a triple bond. Okay, I want to look here at some general statements. In general, for nonmetal elements, the number of unpaired dots is going to be equal to the number of unpaired bonds that an atom can form, right? So if you have 3 unpaired dots, or 3 just 1 dots on each side, then you're going to find that in most cases the element is going to share in order to fill those 3 half-full energy levels, okay? Okay, bonding sites. Nonmetals can be expected to form covalent bonds with each other. An example would be a polyatomic molecule, 3 or more atoms that are bonding together and sharing electrons to form different materials like water, ammonia, methanol. Those would be examples, right? So water would be H2O. You have 2 molecules of hydrogen and 1 of oxygen that are bonding together, bonding to form water. So we see here we have our H2O, H and O. The hydrogen only has 1 valence electron. Hydrogen only has 1 valence electron. But the oxygen, if you were to look on the periodic table, you'd find it to be in group 6A. It's got 1, 2, 3, 4, 5, 6 valence electrons. So it's going to want to get 2 in order to fill its perfect 8. So it's going to take 1 hydrogen here, 1 hydrogen here. So it's going to look like this, a bent molecule. That's going to be what gives water its properties. Okay, ammonia, on the other hand, is going to tend to have more of this kind of a shape, because it's got 3 hydrogens, right? Ammonia is NH3, so it's got 3 hydrogens and a nitrogen. Nitrogen, being in group 5, has 5 valence electrons, so that means it has 3 that are only half full, so it's going to take a hydrogen for each one of those to fill up the spots, and it will have its 8. Methanol has this kind of 1, 2, 3, 4 hydrogens, a carbon, and an oxygen. And we're going to see, though, how we're going to write this out. And I need you to pay attention to this, because C has only 4 valence electrons, so it's got to have 4 filling in. Well, if you thought about it, you could fill in hydrogen on each of those places, but it's not going to allow for the oxygen to get in there. So I want you to see how the OH group, that's going to be the alcohol kind of concept, that the OH group here is going to be a separate group that's going to fill in one of those places. Okay, I just want to look here quickly at the electronegativity difference. Covalent bonds, the sharing of electrons, is going to be related to this idea of a difference in electronegativity. If you were to share with somebody, you have to have the willingness to let them use your toy or your thing, right? But it means that you have something to be able to give up. So there's a difference. You have something that other person does not. So you have to be willing to give or lend, sharing that with another person. A diatomic molecule, right, that would be what we talked about with 2 chlorines bonding together or 2 hydrogens bonding together, is going to have an electronegativity difference of 0, because you have 2 elements that are exactly the same, so example chlorine and chlorine, that have the same exact thing. There's no difference in their electronegativity. That's going to form a nonpolar covalent bond. What we're going to see up here, though, is sometimes bonds that are covalent are going to happen when there's an unequal sharing, right? You have a polar covalent molecule because you have 2 different elements that are sharing those electron pairs, and they're not sharing them equally, right? The electronegativity difference will not be 0. It's going to be different between the different elements, right? Hydrogen often forms highly covalent bonds. One way atoms form covalent bonds affects the molecular structure and shape. Okay, you can have the same exact chemical makeup, right? One carbon and 4 hydrogens, but they can share and make a different pattern, right? A different shape. So there's a tetrahedron, or that's more of a three-dimensional shape. Linear means flat, right? It's straight, like a straight line, right? There are definitely more complex and intricate shapes, and your book is going to show you, different pictures of those. So, okay. What I want to talk about here is weaker attraction between molecules compared to ionic compounds affects their physical properties, right? When we have low melting points, that means something can melt really quickly. It's a sign that there's a weaker bonding between elements. Many liquids and gases are going to fall into this category. Macromolecules, very large bonded molecules together. Some of them are going to be good conductors of electricity, or they might heat well. Good insulators, and the human body has a lot of macromolecules that make it up. In your book, your Dominion Science problem talks about ibuprofen. I would like for you to read about that because it's very interesting. Ibuprofen interferes with the production of your body's prostaglandins. You then can reduce pain and have reduced inflammation because of your body's gaining that ibuprofen. So it's an example of how our science can be connected here to what we're talking about. Thanks. Bye.